Good evening, Samhita.
Good evening, sir.
Have you gone through your notes, ma? Once studied
Yes.
about the atomic structure?
Yes, sir.
Okay. In last class, we were discussing about the photoelectric effect. That means here, Planck's quantum theory and Einstein theory also we discussed. Okay. Now, so these two equations already discussed, and here only we can discuss about the de Broglie wave equation. Here only we can discuss about here de Broglie wave equation. Okay. De Broglie wave equation. So de Broglie wave equation. So what is meant by the de Broglie wave equation means here? So de Broglie is the scientist's name. So he's telling that any small particle, okay, any small particle, it has a dual nature. It has here dual nature. So what is meant by the dual nature means here? So it travels in the form of wave. At the same time, it is in particle in a discrete manner. It travels in a discrete manner. It is not the continuous manner. It travels in a discontinuous manner. Okay, so that's why every small particle it has a dual nature. Sir, what are the dual nature it is having means here? So every small particle travels in the form of wave. Okay, at the same time, it travels in a discontinuous manner. The discontinuous manner and discontinuous species only we can call as either quantum or photon only. Na? Okay, so according to that one, he derived some equation. Okay, so based on Planck's quantum theory. So what is the Planck's quantum theory? What is the equation we wrote as according to the Planck's quantum theory? According to the Planck's quantum theory, according to the Planck's quantum theory, we wrote as a E is equal to h nu. Okay, and according to the Einstein equation, Einstein equation. According to the Einstein equation, what we wrote the formula? E is equal to mc square. Okay, so both energies only. This one is the equation 1 and this one is the equation 2. Now, so both equation, both the energy are same here. If the both the energy are same means we can write as a h nu is equal to mc square. In this one, what is meant by the nu? So nu is nothing but c by lambda only now. So then c by lambda is equal to mc square. If we simplify this one means here, lambda is equal to hc by mc square. In this one, this c is going to be cancelled. So based on that, we can write a h by mc. Okay, so this one in this one, c is nothing but velocity. What is meant by the CMA? C is nothing but velocity, mass and velocity. So mass and velocity means we can write as a h by rho. Also we can write down. So rho is nothing but momentum of the particle. Rho is nothing but here momentum of the particle. Momentum of particle. So based on this one, we are having some questions also. Clear? And one more formula also it is there. So what is the
Yes,
another
sir.
formula we are having in the examination part means here? Lambda is equal to h by square root of 2 into m into ke. 2 into m into ke. So this also it explains the relationship between the kinetic energy and wavelength. The given formula is it explains the relationship between kinetic energy and wavelength. Okay, so based on these formulas also we are having some of the calculations in the examination part. Now you got the clarity, Samhita? Okay. So got it?
Sir.
Right now. So we'll go for the next one. What is the next concept we're having in here? Photoelectric effect. Photoelectric effect. So what is mean by the photoelectric effect? Okay. The next concept we are having is here. Photoelectric effect. Photoelectric effect. So what is mean by the photoelectric effect? What is mean by the photoelectric effect? So photoelectric effect is nothing but ejection of electrons from the metal surfaces by passing suitable frequency of radiation is called as a photoelectric effect. Let us see. First, I am taking as some metal I had taken. Okay, so what I had taken, I had taken as a metal. Okay, so when we are going to pass the suitable frequency of the light, okay, so when you are going to pass here suitable frequency of the light to eject the electron, only we can call it as a photoelectric effect. Okay, and here also we have one more term. So what is another term means here? We have a threshold frequency. Threshold frequency. Sir, what is mean by the threshold frequency means here the minimum amount of energy is required to eject the electrons from the metal surface is called as a threshold frequency. Threshold frequency can be represented with nu naught. How we are going to represent the threshold frequency, ma? Threshold frequency can be represented with nu naught. Now we got the clarity. Okay, so what is meant by the threshold frequency means here? Threshold frequency is nothing but the minimum amount of energy is required to eject the electron from the metal surface is called as a threshold frequency. Okay, according to that one, let us see. Here, if you pass excess high frequency of the light, if you are going to pass high frequency of the radiation on the metal surface means, okay, how much energy is required to eject the electron, that it is going to be taken, and the remaining excess of energy is converted into the kinetic energy. The remaining excess of amount of energy is called as a kinetic energy. So based on that one, how we are going to represent the mathematical, how we are giving as a mathematical expression means here, first energy is equal to E. Okay, E is equal to, we are passing high frequency of the radiation. When you pass high frequency of the radiation means some energy is took to eject the electron. Whatever the frequency it took to eject the electron, that we can call as a work function. That we can call as a work function because of it removes the electron from the metal press. That's why we can call as a work function. Whatever the additional energy you passed on the metal surface, that we can call as that it is converted into kinetic energy. Okay, sir, how we can represent the work function means E is equal to, work function can be represented with H nu naught plus Ke. Then what about the E? Energy also it is nothing but H nu only na. Hence H nu is equal to H nu naught plus Ke. So if you take all frequencies at one side, if you take all frequencies at one side means H nu minus nu naught is equal to Ke. Okay, so nu minus nu naught is equal to Ke. So this is the formula. So based on that one, we are having some of the calculation. Sir, which metals are they undergoes to the ejection of the electron? Question number is here. So what is the question means? Which metals are they undergoes to the photoelectric effect means here? The metals which are having low ionization enthalpy. In a whole periodic table, which elements are having low ionization enthalpy? Any one of you? Which elements are having low ionization enthalpy in a whole periodic table? Cesium is having the least ionization enthalpy in the whole periodic table. So which metals are they taking the photoelectric effect means here? Potassium, rubidium and cesium. Okay, so potassium, rubidium and cesium are they take under they undergoes to the photoelectric effect. Why they undergoes to the photoelectric effect means because of they're having the low ionization potential. Okay, now we got the clarity. Now we got the clarity here,
Yes, sir.
all of you. Right now. Now conditions are there. So what are the conditions they are giving means they're comparing the frequencies. That means they're asking nu and nu naught. Okay. If nu is greater than if nu is greater than that of the nu naught, that means the frequency is greater than that of the threshold energy. Either the metal is it undergoes to the ejection of electrons or not, or metal is ejects the electrons or not. Metal is eject the electron or not. Can you answer, ma? Can you answer, ma? Frequency value is greater than that of the threshold energy. Samhita,
Sir, could you repeat the question?
once again I'm asking the question, ma. I had given frequency and threshold energy. Okay. So threshold energy also I had given and frequency also I had given. What is the condition means if frequency is greater than that of the threshold energy.
Then only electrons will get emitted out.
Electrons are emitted out or emitted electrons cannot be emitted out.
They will be emitted out and they'll possess kinetic energy too.
Very good, ma. So electrons are emitted out. That means ejection of electrons will take place. Okay, ejection of electrons will take place. Ejection of electrons will takes place. It takes place. Okay. Now another condition. So what is the another condition means here? So nu naught and nu one. So now nu is less than nu naught. Then what about the condition here? If ejection of electrons will takes place or not? Frequency is less
Ejection
than
will
that of
not
the
take
threshold
place.
frequency. Ma?
Electrons will not be ejected.
Ejected, ma. Electrons are not ejected here. Okay, ejection of electrons does not takes place. Okay, does not takes place. So why it does not takes place means here because of frequency is very less. If the frequency is less means electrons cannot be come outside. So minimum frequency of the minimum frequency is required to remove the electron. That is only we can call as a photoelectric effect. Now you got the clarity, all of you. Okay, so based on this formula also we're having some of the calculations, and sometimes they're asking the condition periodical base means multi-correct answers means here based on the cases here. If frequency is nu is greater than that of the nu naught, what about here? What happened? If nu is less than that of the nu naught means what happened? That kind of questions they're asking. Now got the clarity? Okay, then
Yes, sir.
photoelectric effect is finished here. Then we'll go for the Heisenberg uncertainty principle. Then we'll go for here Heisenberg uncertainty principle. Heisenberg uncertainty principle. Uncertainty principle. So what is the Heisenberg uncertainty principle, ma?
We can't find the position and the momentum accurately at the same time.
Very good. Okay. So what is the formula? What is the mathematical expression of the Heisenberg uncertainty principle means here? Delta x into delta p is greater than equal to h by 4 pi. This is a mathematical expression. In this one, delta x is nothing but position, exact position. It represents as a exact position. Then delta p also we can write as m into delta v. So generally this we can call as here momentum. This we can call as a momentum. Okay. According to the Heisenberg, it is not possible to calculate exact position and exact momentum at a time. Okay, so how we can calculate means exact position and exact momentum are calculated simultaneously. It is not possible to calculate exactly at same time. Whether it is correct or not, ma? Whether it is correct or not statement. Okay, so he's telling that if you are going to identify the exact position means momentum, it will be different. Momentum, it will be different. Okay, if you're going to calculate the exact momentum means position is going to be different. Okay, sir, what is the best example for that one means here? Whenever you are in traveling, okay, so whenever you're traveling, if somebody somebody they're asking your exact location, is any possibility is that to tell the exact location when you are in traveling, bus is moving, keep on moving only. Is any possibility is that to tell the exact position? Sriyuta, Samhita J. You all are going to the school, ma. Somebody they called, one of your friends they called, and they asked, where are you? Is any possibility is there to tell the exact position?
No, sir.
No, ma, it is not possible. If you tell one address means buses keep on moving only. It is not at one particular place. Okay, so whenever it is keep on moving means whenever you give the address means within fraction of second that address is going to be changed. Okay, or otherwise if you tell exact position means then whatever the momentum is going to be changed. If you want to tell means here, so for example, you are riding bike in with 60 kilometers of the speed. Somebody they called and they asked, so what is your exact position means? To tell the exact position, automatically your speed is going to be down, right? So momentum is going to be changed whenever you are going to tell the exact position. So one you are going to tell exactly means another one it becomes as a infinite. Okay, so due to that reason only here, it is not possible to calculate exact position and momentum at a time. So we can calculate simultaneously. Now we got the clarity. Okay,
Yes, sir.
and what is the another important concept we are having in this chapter means here quantum number. Okay, so before going to the quantum numbers, one more hydrogen spectrum also it is there. Hydrogen spectrum. Hydrogen spectrum. Do you have any idea about the hydrogen spectrum? This is now we can call as a hydrogen spectrum. So this we can call as a hydrogen spectrum. Sir, how we are getting as a hydrogen spectrum means in Bohr's atomic model we had seen. In this one, what is the N1, N1, N2, N3, N4, N5, R, N6 and at all here? They represent as the energy level. First energy level, second energy level, third energy level, fourth energy level, fifth energy level, sixth energy level, seventh energy level and all. Okay. Now let us see when the electron is jumps from high energy level to lower energy level, that it emits the radiation. Okay, it emits a radiation. Whatever the radiation it is emitted, that we are going to see in a visible region. Whenever you're going to see in a visible region means then only we can find out the color. Okay, so what are the spectrum based on the transfer of the electron from one energy level to another energy level? It forms as a spectrum. That is only we can call as a hydrogen spectrum. In hydrogen spectrum, what are the series are there means here? Lyman series, Balmer series, Bastian series, bracket series, Pond series here. Okay, now Lyman series can be observed in an ultraviolet region. So where we can observe as a Lyman series, ma? Lyman series can be observed in a ultraviolet region. Okay, and here Balmer series can be observed in a visible region. Paston series can be observed in a near infrared region. Bracket series can be observed in a infrared region. Okay, and point series can be observed in a far IR. Okay, far IR. Now, first you can check it out here in Lyman series. What is the N1 value? Means N1 value is equal to 1. Then what about the N2 values? N2 values is equal to either it may be 2, 3, 4, 5, 6. Okay, and for the Balmer series, what is the Balmer series? N1 value means N1 value is equal to 2 for the Balmer series. Okay, so Balmer series here. So what is the N1 value means? N1 value is equal to 2. And what are the N2 values means here? N2 is equal to 3, 4, 5, 6, 7 like that here. Then Paston series. N1 is equal to 3. Then what about the N2? N2 is equal to 4, 5, 6, 7 and so on. And bracket series. N1 is equal to 4. Then what about the N2 value? N2 value is equal to 5, 6, 7, 8. Okay. And fund series. N1 value is equal to 5. N2 value is equal to 6, 7, 8, 9 and so on. Sir, why we have to know N1 and N2 values here to calculate the wave number? So by using the hydrogen spectrum also we can calculate the wave number. Sir, what is the formula we are using to calculate the wave number? Means wave number is equal to 1 by lambda is equal to R into Z square into 1 by N1 square minus 1 by N2 square. By using this formula, we are going to calculate the wave number. So to calculate the wave number means compulsory we have to know now what is the N1 and what is the N2 value. Because of every series N1 and N2 values are different it is there. Okay, all series are not having same N1 and N2 values here. Okay, all series are having here different N1 N2 value. If you know the N1 N2 value means based on that one we can calculate. Okay, in this one, sir, what is mean by the R? R is nothing but it is a Rydberg constant. What is mean by the R my here? R is nothing but here Rydberg constant. Okay, so Rydberg constant. So what is the Rydberg constant value? 109677 here. So 109677 is called as here Rydberg constant value. In this one, Z is nothing but atomic number. In this one, Z is equal to atomic number. Z is nothing but here atomic number. Okay, and if you substitute all the values means we can calculate the number of waves, and sometimes they're asking to calculate the wavelength also. Okay, now we can calculate now if you know the wave number means from that one we can calculate the wavelength also. Okay, so now you got the clarity all of you. Clear? Again, here only we are getting in quantum numbers only we are getting as a N1 value. Okay, so what is the next important concept we are having means here? Quantum numbers. So do you know about the quantum numbers, ma? What is meant by the quantum numbers? Give me one of you. What is mean by the quantum numbers? The quantum numbers are give exact information of electron in an orbital. So quantum numbers are, they give exact information of electrons in an atom or in an orbital. Okay, so generally in an atom. Okay, so we don't know where the electron it is at. So that which one they are going to tell exactly means here. So quantum numbers are, they give the exact information of the electron in an atom. Clear? Okay. Now, sir, how many types of the quantum numbers we are having? Means we have 4 types of the quantum numbers. So one is principal quantum number. Principal quantum number. Okay, principal quantum number. Sir, what is the principal quantum number and who proposed the principal quantum number? Means principal quantum number is proposed by the Niels Bohr. So who proposed the principal quantum number, ma? Principal quantum number is proposed by Niels Bohr. Sir, how you are going to represent the principal quantum number? Means principal quantum number can be represented with small n. How we are going to represent this principal quantum number? Principal quantum number can be represented with small n. Okay, got the point? Okay, so what is the main importance of the principal quantum number? What is the significance of the principal quantum number? Means principal quantum number is, it explains size of the atom, size and energy level, size and energy level of atom. It explains here size and energy level of the atom, or it explains size and energy level of the orbit. Okay, size and energy level of the orbit. Now, in this one, if the n value is increases, if n value is increases, n value increases, size is going to be increases or decreases? If n values increases, then what about the size? Size is going to be increases or decreases? Size is going to be increases. Okay, so based on that one, we can calculate the number of orbitals. First, we can calculate the angular momentum of an electron. So what is the angular momentum of the an electron? Means angular momentum of the an electron, MVR is equal to NH by 2 pi. MVR is equal to NH by 2 pi. Okay, and here we can calculate the total number of orbitals. We can calculate total number of orbitals. Total number of orbitals. So what is the formula they are using to calculate the total number of orbitals? Means n square. Okay, so what is the formula they are using? Means here they are using to calculate the total number of orbitals is equal to n square. For example, if n is equal to 1, then total number of orbitals is equal to how much, ma? 1 only, na?
1.
Okay, if n is equal to 2 means the total number of orbitals?
4.
4. Okay, if n is equal to 3 means total number of orbitals?
9.
9. Okay, if n is equal to 4 means total number of orbitals?
16.
16. Okay, total number of orbitals is equal to 16. Sir, how you are telling that the total number of orbitals means here? So one in first energy level, one orbital means 1s. Second energy level, total number of orbitals is equal to 2s and 2p. How many subshells are there for the p orbital? Means 3 subshells are there. How many subshells are there for the p orbital? Means here? So p orbital is having 3 subshells. Okay, and if you see total number of orbitals in third energy level is equal to 3s, 3p and 3d. The total number of orbitals per d orbital is equal to 5. 5 plus 3 plus 1. 5 plus 3 plus 1, how much, ma? 9 only, na? And fourth energy level, 4s orbital, 4p orbital, 4d orbital and 4f orbital. 4s, 4p, 4d and 4f orbital. Okay, the number of subshells present in 4f orbital is equal to 7. The number of subshells present in 4d orbital is equal to 5. The number of subshells for the 4p orbital is equal to 3. The number of subshells for the s orbital is equal to 1. If we calculate the total number of orbitals, ma, how much you got? Got as a 16 or not? Okay,
Yes,
and we
sir.
can calculate the total number of electrons also by using the principal quantum number. So how we can calculate the total number of electrons? Total number of electrons is equal to 2n square. The total number of electrons is equal to 2n square. Now we got the clarity. All of you got it?
Yes, sir.
Okay. Next one. Azimuthal quantum number. Azimuthal quantum number. Okay. My azimuthal quantum number is proposed by Sommerfeld. Okay, Sommerfeld. Azimuthal quantum number is proposed by Sommerfeld. Azimuthal quantum number can be represented with small l. Azimuthal quantum number is depends upon the n value. Depends upon L value. Depends upon n value. Which one means n value? Then based on that one, how we can write means L is equal to n minus 1. L is equal to n minus 1. In this one, if n is equal to 1 means it represents as a s orbital. That means whatever the L is equal to 0. If n is equal to 1 means then whatever the L value is equal to 0. If it is 0 means it represents as a s orbital. If n is equal to 2. If n is equal to 2 means then whatever the L value, L is equal to 1. If L is equal to 1 means it represents as a p orbital. Okay. If n is equal to 3. If n is equal to 3 means then whatever the L value is equal to 2. If L value is equal to 2 means it represents as here d orbital. If n is equal to 4, then L value is equal to 3. L value is equal to 3, it represents as a f orbital. Okay. So what is the main importance of azimuthal quantum number means azimuthal quantum number it explains subshells. Okay, explains here subshells. Explains here subshells. Whatever the s orbital, p orbital, and at all here, all these are we can call it as a subshells only. Okay, clear? So based on the azimuthal quantum number, we can calculate the angular momentum. Angular momentum also. So what is the angular momentum of an electron with respect to the azimuthal quantum number means we can write as L into L plus 1 h by 2 pi is the formula. So what is the formula we can write square root of L into L plus 1 h by 2 pi is the formula. So based on that one in JEE they asked one question what is the angular momentum of an electron and they had given the azimuthal quantum number value. Okay, if they had given the L value means from that one we can calculate or not? Can calculate or not? Okay, so we can calculate the angular momentum. Okay, next magnetic quantum number. Magnetic quantum number. Okay, so magnetic quantum number. Magnetic quantum number is proposed by Landé. Okay, according to the magnetic number, magnetic quantum number can be represented with small m. Small m is depends upon L value. Depends upon L value. Then the m values are plus or minus L including 0. Including 0. Okay. So my m values are plus or minus L including 0. For example, if L is equal to 1. If L is equal to 1 means how we can write means here m is equal to minus 1, 0, plus 1 we are writing values. Sir, what are the minus 1 and 0 plus 1 means here? Magnetic quantum number is it explains the spatial orientation. The spatial orientation. Spatial orientation of electron. It explains here the spatial orientation of the electron. Based on this one only, we can say p orbital is containing how many subshells means here p orbital is containing 3 subshells. What are the 3 subshells means px, py and pz. What are the subshells we are having means here px, py, pz. So like that d orbital also. If you see for L value, if L is equal to 2 means, then what about the M values we can write? M value we can write as a -2, -1, 0, +1 and +2. Okay, so generally L is equal to 2 means it represents as a which one ma? D orbital only na? In D orbital, how many subshells are there? 5 subshells are there. What are the 5 subshells we are having means dxy, dyz, dxz and dx square minus y square and dz square. Okay, and if L is equal to 3, if L is equal to 3 means what about the M values we can write? M values we can write as a plus or minus 3 including 0. Okay, so this one it represents as a F orbital. Total number of subshells present in F orbital is equal to 7. Total number of F orbitals present, total number of subshells present in F orbital is equal to 7. So magnetic quantum number is to explain the spatial orientation of the electron. Okay, so based on that one only we can explain the shape of the orbital. Okay, based on this one only, based on the orientation of the electrons only, we are going to explain shape of the orbital. S orbital is having which shape, ma'am? Spherical shape. P orbital, what is the shape of the s orbital? S orbital is having spherical shape. P orbital is having dumbbell shape. Okay, and D orbital is having double dumbbell shape. Okay, F orbital is 3D here. F orbital is having 3-dimensional axes. Clear? So now you got the clarity, all of you, everyone.
Yes, sir.
Next, so what is the another quantum number we are having means here spin quantum number. Okay, spin quantum number. Spin quantum number is proposed by the Gauss-Smith and Uhlenbeck. Okay, spin quantum number can be represented with S. Actually, we have two spin values. So what are the two spins? One is having plus of, another one is having minus of. So spin quantum number is it represent as a position of the electron. Okay, that means in each and every orbital. So how maximum number of electrons are accommodated in the one orbital is equal to 2. In that one electron is present in the clockwise direction, another electron is present in a anti-clockwise direction. So one electron is present in a clockwise direction, then we can represent as a plus of. If the electron is present in an anti-clockwise direction, that we are representing as a minus of. Okay, clear? Clear? And spin angular momentum. What is the formula we are using to calculate the spin angular momentum? Means here S into S plus 1 h by 2 pi. H by 2 pi. So by using this formula, we are going to calculate the spin angular momentum also. Okay. Now in this one, if you see what is the main importance of the spin quantum numbers means for any electron. Okay. 3 spin quantum numbers are the same and the fourth one is going to be different. Okay, for any element, so 3 spin quantum numbers are the same, but the fourth one is different. Sir, which one is going to be different means here spin quantum number. So because of spin quantum number, we does not predict exactly. Okay, spin quantum number, we cannot predict exactly. So because of which position it is there or not, we can't find out. How you going to find out means based on the electron spin resonance spectroscopy, we can find out here. Okay, so how we are going to find out the direction of the electron means here based on the electron spin resonance, we can find out the spin electron direction. Okay, so this is about atomic structure. So after that also we are having some concepts. What are the concepts we are having means here Harbour principle, Pauli exclusion principle, and Hund's rule. What is the Harbour principle? Any one of you? What is the Harbour principle? Do you have any idea, ma? Any one of you? You're writing electronic configurations, Nama. All of you don't know how to write the electronic configurations. What is the electronic configuration of the sodium? Sodium atomic number is 11. We can write as a 1s2, 2s2, 2p6, 3s1. This is only the electronic configuration. Na? How
Yes,
we are
sir.
writing this electronic configuration means based on Avro principle. Avro principle. Sir, what is meant by the Avro principle? Means Avro principle is to explain filling of electrons in an orbital. Sir, how we can explain means filling of electrons can be explained based on the molar diagram. That means 1s, second energy level we are having 2s, 2p orbital, third energy level 3s, 3p, 3d, and fourth energy level we are having 4s, 4p, 4d, and 4f. Fifth energy level we are having 5s, 5p, 5d, 5f. Sixth energy level we are having 6s, 6p. Okay. Now, sir, how we can fill the electrons means first the electrons are enters into the lower energy orbital. That means first electron is enters into the 1s orbital. After filling that, the electron is enters into the 2s orbital. After filling the 2s orbital, the electrons are enters into the 2p. After that, 3s. After that, 3p, 4s. After that, 3d. Okay, 4p, 4s. But in your NCERT textbook, while writing the electronic configuration of the 3D series elements, they wrote as a 3D orbital is first. They wrote as a 3D orbital is first. Okay, but you won't get as a 3D orbital first one. Okay, sorry, 3D orbital only will get as a first here. Clear? Actually, how we can write means here 3, 4 is 2, 3D mark here. 4 is 2, 3D. Okay. Clear? After the 4s only, electron enters into the 3D orbital. So once you checked out the electronic configurations, and Pauli exclusion principle. What is meant by the Pauli exclusion principle means here, no two electrons can have same set of 4 quantum numbers in orbital. What is meant by the Pauli exclusion principle, ma? Pauli exclusion principle is nothing but, so no two electrons can have same set of 4 quantum numbers. That is only I told that. So 3 are same. The fourth one compulsory it will be different because of in one orbital maximum we can accommodate as a 2 electron. So 2 electron means one is present in a clockwise direction, another one it will be present in a anti-clockwise direction. So if first 3 quantum numbers are same, but the fourth quantum number is same or different, ma? The fourth quantum number is different only now. So what are the fourth quantum number we are getting means one is exhibit as a plus of, another one is exhibit as a minus of. Okay. And Hund's rule. What is meant by the Hund's rule? Hund's rule. What is meant by the Hund's rule? So Hund's rule explains as a degeneracy. Degeneracy. So filling of electrons in degenerate orbitals. So what is meant by the degenerate orbitals means the orbitals which are having same energy. The orbitals which are having same energy. Same energy is called as a degeneracy orbital or degenerate orbital. Sir, what are the examples for that one means here p orbital? P orbital is having 3 subshells. What are the 3 subshells means px, py, pz. So all these px, py, pz are having equal energy. Sir, how we are going to fill the electrons in the degenerate orbitals means first one electron is enters into the each and orbital. After halfly filled, then only pairing it takes place. After halfly filled, then only pairing it takes place. The maximum number of electrons present in p orbital is equal to the maximum number of electrons present in p orbital is equal to how much, ma? Samhita?
6.
The maximum number of electrons present in p orbital. How many electrons are there? Samhita J.
6, sir.
Very good, ma. The maximum number of electrons present in d orbital is equal to
10.
10, sir.
maximum number of electrons present in f orbital is equal to
14.
14. In that half means ma 3 na. In d orbital half electrons means
5.
5. In f orbital half electrons means 7. So after filling of the 3 electrons only, then only fourth electron it is going to be pairing. Fourth electron is here pairing. Okay, and one more statement also it is that. So halfly filled orbitals and completely filled orbitals are more stable. So which are more stable? Halfly filled orbitals and completely filled orbitals are more stable. In that also, if you compare with the half filled and completely filled, means completely filled orbitals are more stable. Now we got the clarity, all of you.
Yes, sir.
Okay, so this is about structure of atom. Okay, so next, so tomorrow we will discuss the new chapter. So tomorrow I'm going to discuss about the classification of elements. Okay, ma? Clear?
Yes, sir.
So that thank you all, ma. So once you read today, you finish this concept, and so already got some assignment. First you practice some questions. Okay,
Okay, sir.
then we'll continue in the next class. Thank you all.
Thank you, sir.
Thank you.
You're welcome.